Assalamu alaikum. Welcome to lecture 14 of natural language processing. I hope all of you are doing well. So we have completed 13 lectures of this course so far, and we have also done our midterm exam. So we are actually into the second half of our course. So before the mid, we were discussing feed-forward neural networks. We had talked about the basic building blocks of the feed-forward neural network, and we also briefly discussed the terminology and the basic computations or that are required for inference using a neural network. So the idea for today is I will complete this discussion on feed-forward neural network, and we will discuss briefly training and also some issues and their resolutions that are typically used in modern day neural networks or deep learning networks. And after that, we will start with uh, vector representations of linguistic units, and which of course would also lead back to neural networks again later on. So, so that's the idea. So we'll kind of wrap up the introduction to feed-forward neural networks and then go back to learning vector representations or embeddings for linguistic units like words. uh, so in your course, you also have a project. So I'll be sharing the information for the project later this week. The project would be a group project, and the general idea would be that you will be picking 2 or 3 papers and trying to re-implement a paper of interest. And so it's a kind of implementation project, but implementation of some recent technique or approach that has been proposed in the NLP literature. So I have reduced the scope of the project somewhat, so that's why we are starting it a little bit late. So we won't have a detailed literature review or a detailed methodology. It will be more of a implementation of some recent research work. So, so that would be your project, and I will share the details later on. You may go ahead and form groups. I think we have about 30 students, and you can have a group of up to 3 people, not more than 3 people. And of course, if you are interested, you can do the project independently as well as individual. All right, so I think with that, let's get started. Any questions? Any questions? So we were discussing the feed-forward neural network and the basic processing unit. I think the caps lock is on. What's happening? All right. So the general basic processing unit of a neural network, a single unit, gives you an output A, which you can also call it an activation. Uh, the activation of the output of the unit A through some function G. You have some input which is passed through or weighted through some weight vector W. You can think of this an inner product of W and X. These two are vectors. And then you have a bias term. If you are explicitly dealing with a bias term, you so this is basically the single unit of a basic neural network. And if you compare this with the binary logistic regression, it's identical. It's almost the same. G would, of course, be the sigmoid function. So it is a sigmoid. And then the bias B is actually W naught. So if you remember in when we wrote the logistic regression model, we wrote it as W naught plus W1 X1 plus W2 X2 plus so on. And of course, W naught plus W as a vector, which does not include W naught and X as a vector. So this can be written as in this way, which is kind of the same thing that we have written here, B plus W into X. All right. So the bias basically is required, and for most applications, it's basically a weight vector that is not dependent on the input. And that kind of moves the line. If you think of this as a plane or a hyperplane, it moves the plane up and down. Or in other words, it translates the plane. So we want to find the best plane that does our job. So we need this flexibility as well. And this flexibility is thus provided by this weight parameter or the bias parameter. So let's say if you have multiple output units, then A would be a vector, and then again G, and then all the weights to all the units would be put into a matrix W, and then you have the input X, and then B would then of course be a vector. So again, the formulation is exactly the same or similar, only that the variables that you have now are have higher dimensions. So so let's say we are talking about let's say K units. Okay, so then A, B, and of course X is A and B are K, D vectors, and W would be what? W would of course depend on the input. So let's say X is, let's say you can say N D input vector or activation vector from the previous layer. And then we have our W, which is a weight matrix. So this would then be, so we have the output as K times N matrix. All right. So sometimes we will not write the bias vector explicitly. We will include it into the matrix W. So in that case, W would then be, you have, of course, K rows, which is of course the number of output units, times then N plus 1. So there is one additional input which is clamped to the value of 1, which has the parameter given in this column, usually the first column of this matrix. So you can not write the bias parameter explicitly. You can include it as a column in the matrix W, the first column of the matrix W. And you can actually verify that you will get the same result from both calculations, where you have B vector as separate, that is adding to the multiplication of W into X, and this augmented, you can say, matrix W, where B is put into the first column. So we'll get the same result. So sometimes for notational simplicity, we would not write B explicitly and include it into W. All right. So a feed-forward neural network basically does consist of multiple layers of such units. And we talked about, let's say, if you have a 3-layer network. So the first, of course, is the 0th layer, which is also the input. And then we have the first layer, which is also called the hidden layer. And then the second layer, this is also the hidden layer because inside the network. And then you have the third layer. This is, of course, the output. So sometimes you notice that we have mentioned hidden layers. So the input and output are sometimes also called visible layers. So those layers are visible to the outside world. The hidden layers are within the sequence of layers, and they are not visible to the outside world. So, so the two hidden layers. So basically, a 3-layer network would have 2 hidden layers and 1 output layer. So we usually don't count the input layer as part of the size of the feed-forward neural network. We call that the 0th layer. All right. Mm. And you will find various notations that are used. Uh, so we can say the weight matrix for the first hidden layer to be W1. So this is matrix for first layer. So in the book, they have used the notation W superscript of 1 in brackets. So this is more cumbersome to write, so I might just write W1. All right. Similarly, so if you have, so that would be the, and of course, B1 would be the bias for the first hidden layer. Of course, this would be a vector if the first hidden layer has N1 units. So basically, N1 is the number of units in first layer, which is, of course, the hidden layer. Okay. So this is the notation, and then A1, you can also call this Y1, but I think to be consistent, I've used A1 activation as the output of first layer. So the X is input to the network, the entire network. So this is the input to the input layer, and Y is the output of the network, which is the output of the output layer. So you can also think of Y as being equivalent to, let's say, if it is a 3-layer network, so this would be A3 for 3-layer network. Okay? But we usually use the variable Y to denote that this is the output of the whole network. X is the input of the whole network, and the outputs of the inside layers are given by A or activations, A1, A2, A3, and so on. All right. And biases and weight. So what are the parameters of this network? So the parameters, so basically all W's and B's. All right. Okay. So these are the parameters of the model which we would have to learn. And since a feed-forward neural network is a supervised learning model, we will assume that we have training data. And if it is a classification problem, then of course the training data would consist of basically training data. If I want to write it, it's basically a set of xi and yi, where I is equal to 1 to n. basically we are using n for something else as well. So you can say, I think I'll just use n here as well. We call that n1, n2, n3. So this is n. So n is the number of training examples. So x is, of course, the input vector. Y is the output. So for a k class problem, so this would be a value from 1 to k. And if it is a binary class problem or 2 class problem, this would be a binary variable, which would be 1 for the one class and 0 for the other class. Okay. So, so of course you have this training data, and just to distinguish that y is the true value that I've written here. So the output of the network, I can call that y prime. So this is the so the output of the network is y prime for any given x. For any given x, you have the true value y. Just give me a second. So if y is the true value, so this is the true value of a given x, then of course y prime is the output, the predicted value. So obviously we would like to have a model which would give you a predicted value identical to the true value. Of course, so that's of course the goal. And just give me a second, let me turn off my phone.
Button. Device lock. Lock screen. Use fingerprint or swipe with 2 fingers to unlock. Device 1 UI home. Chrome. 1 UI. Notification. Wi-Fi on. Air. Sound on. Button. Vibrate on. Vibrate on. Button. Mute on.
All right. All right. All right. So we would like to have the predicted value to be as close as possible to the true value for any given x or for all possible x. So obviously, we have a training data set. So on the training data set, we would like to minimize this difference, and that difference is usually quantified as an objective function or a loss function. So loss function, you can call it an objective function. All right. And for classification, we use the cross entropy as a loss. So you can extend this for multi-class classification problem as well. So binary cross entropy, or for multi-class problem, we call it the multi-class cross entropy. So this is the objective function. The objective function or loss function is this a function of all the parameters W, all the W's and all the B's. So we would like to minimize this loss and find the best possible values for W and B. So once you have minimized that function, you will get the optimal values for W, which I can say is W star and B star. So once W and B are fixed, W star and B star are found, your neural network is trained. Once your neural network is trained, you can use it to make predictions for new inputs. Okay? So you be using these values for W and B while you're doing the inference. Okay? All right.
Yes, sir.
Question?
Yes, sir.
जी.
सर ये जो बायस का पैरामीटर होता है ये भी हम लर्न करते हैं
बायस का पैरामीटर कैसे बोले?
मतलब मैं कह रहा हूँ द बायस पैरामीटर डू वी लर्न दिस एज वेल मतलब हम इसको भी
जी जी,
अपडेट कर रहे
yes,
होते हैं
yes.
ओके
So bias is also a parameter. So in a way, bias is just like any other weight. So in fact, as I mentioned earlier, you can write the bias separately, or you can even include bias in the matrix W as the first column of the matrix W. Okay. So it is a parameter that is learned as part of the optimization process. And we will not go over the details of the optimization. I'll just give you the brief outline and so that you get the understanding. So we basically use the stochastic descent approach, which is a iterative optimization technique. And the general idea here is that you do multiple iterations. You have some current value of the parameter. Let's say we are talking about parameter W or one parameter W, let's say. So this is the new value, let's say, would be given by the old value in the previous iteration plus minus, we have a parameter eta multiplied by the gradient of the loss function with respect to this W. Okay? So actually gradient with respect to W of the loss function. Okay. Okay, so basically, you are using this approach. So we are finding the gradient of the loss with respect to this parameter. Gradient is what? Is the slope of the loss function or loss surface. It of course would be in higher dimension. So it's a surface. So at the particular point W, or sorry, at the, so we want to find the gradient at the particular value W. So this would be, a gradient always points to the position of, you can say, ascent. So it's in the positive direction. So that's why we have the negative, and eta is a parameter, which is, so eta is always greater than equal to 0, it's always be 0. So this is the step length. So the length by which you want to move in that direction. So of course, gradient is a direction that points to the highest or peak of the slope of the function. So we want to move in the negative direction. So we have the negative there, and we want to move by the amount eta. So eta here is the parameter, which of course in this setting would become a hyperparameter, a parameter of the parameter, because our parameters are W and B. But to solve that or to find those parameters, we have to use some approach which requires other parameters. So such parameters called hyperparameters. Okay. So So we will use this iterative approach until W does not change from one iteration to the other, or in general for a few iterations, or the change is within some constraint. So in other words, if I want to write this, so uh, some norm, if of course, if W is a scalar, then it's absolute value simply. So W new minus W old is less than some epsilon, some small value. If this is less than this small value, then we stop, and that W would become our optimal W. Okay? So this is done over the training data set. Okay? But there are some things that you need to consider, which I'll discuss now. Of course, here, of course, if W, you can think of this W as a scalar, in which case is absolute value. If it is not scalar, you can think of this as a vector or a matrix. Then this would be a norm, like an L2 norm, the sum of the squared differences between the two values. Okay? So some norm. So norm would give you a scalar. Okay. So the stochastic gradient approach, the one I mentioned, where we had the new value and the old value. So this, in the truest sense or the purest sense, is updated after you feed in every example or each example into the network. So we have various examples. Let's say you have x1. This is one example, and it has its corresponding y1, right? And then we have x2, and we have the corresponding y2, and so on until, as we said, we have n training examples and the corresponding y. So whenever you feed one of the training examples, you update the weight matrix, or you update all the weights. So there are tons of weights in the neural network. You update all the weights using that formula. So we'll come back to back propagation shortly. I just want you to understand the idea of update first. Okay? So you will update the weights. Okay? So you have to update these weights after each example. But usually that is becomes quite tedious. Usually the number of examples in our training set is huge, and you're doing update after feeding one example at a time. So what we typically do is we typically do batch updates. And sometimes if the batch size is, so batch could be a bunch of examples that are fed at once. All the changes are accumulated, meaning that if you feed one X, you will get one Y, and there will be some error between the true Y and the predicted Y. You feed in another X, you get another error. So you sum up all the errors. And the sum of all those errors are then updated at once after seeing all those examples. So this is called batch mode. You don't update the network after each example, you update the network after seeing a batch of examples. So let's say, so after B examples, okay? And of course, B would be less than N, where the N is total number of examples. So sometimes we also call this as a mini batch. In the literature, we see this as mini batch. Usually mini batch means that the batch size is not very large, nor it is very small. It's somewhere in between, and usually kept uh, to the size of the cache memory. So of course, that is approximate. Usually no one does it accurately or exactly. So sometimes, let's say 128 examples, or let's say, uh, or 512 examples, so on. So these are also sometimes also called mini batch. So in other words, what I'm trying to mention here is, you, rather than updating your network after each example, you update the network after feeding in this number of examples, which is, let's say, 128 or 512 or any other number B. So all of those errors are accumulated and then the model is updated. Okay? So in practice, we do batch updates rather than incremental updates after each example. So that was one thing. The other thing that I wanted to mention briefly, again, we won't go into the details, is the issue of back propagation. Remember, I mentioned the loss y and y prime. Y prime is predicted, y is the actual value. Where do you see y prime? So this is at the output layer. And at output layer, you can compare it with y and of course get the exact error. But what about the hidden layers or the inside layers? So you have, let's say you have a 3-layer network. So you have an output A1, which is output of the first hidden layer. Then we have A2, and then of course you have Y prime. So for Y prime, you have the exact error or loss because you know the true value Y. And then of course, using that, you can update, of course, W2 and B2 directly using the stochastic gradient approach because you have the loss. But what about, for example, so W3 होगा, sorry, because 3-layer network मैंने कहा था ना, ठीक है? So what about W2? So how do you have that loss there? So you have to do a bit of computations. Essentially, we use what is known as error back propagation, meaning that the error at the output layer is apportioned to the hidden layers as well. And those errors are then used to adjust the hidden layers parameters. Okay? And this whole process is basically called error back propagation. And this is a very famous algorithm. So which is sometimes also abbreviated simply as BP. So this algorithm was, I think, first proposed earlier in the 70s, but I think it really became popular in the 1980s and became the you can say the backbone of modern day neural networks and deep learning. So essentially what it is, output layer में आपके पास true value भी है, predicted value भी है, वहां से आप loss निकाल सकते हैं, error निकाल सकते हैं. उस layer की आप parameters update directly कर सकते हैं using the stochastic gradient descent approach. But what about the hidden layers? So उसमें क्या होता है कि जो loss आखिरी लेयर क्या है वो आप appropriately apportion करते हैं, of course through a mathematical approach using gradients and chain rule to the hidden layers. So जो loss output layer में था वो आपने input layer पे कुछ दिया आया, वो loss लेके आपने फिर hidden layer की weights update किए, वो और पीछे गया, आपने you go back until you reach the input layer. So in this way you update all the weights in the neural network. So in other words, during inference, information flows from left to right, from input to output. But when you're training and updating the model, information flows from the output back to the input. So that's why this is called back propagation. So information flows from the output where you have the true and the predicted value difference. So that is the error. So that information are flowing back to the network to update it, to adjust the parameter W and B. Of course, the derivation for this isn't that technically difficult. Simply use chain rule and derivations, but notation-wise, it might be complicated, especially for deep networks. ठीक है, तो वो आप would not include it as part of this course. Deep learning and network के course में पढ़ लेंगे. But you need to understand the concept. So any questions on this? Okay, in the stochastic gradient descent, I mentioned gradient with respect to W of the loss function, right? So this was the value that was making the change. So if this gradient was zero, then there would be no change. Remember, W new is equal to W old minus eta into gradient. If gradient was zero, then there would be no change and you will stop. Or meaning that from one iteration to the next iteration, there will be no change in W, the parameter W or the parameter B, if you are using different notations. Okay? So how is this gradient determined? So the gradient actually depends very heavily on the activation function that you have used. And of course, you can do this exactly using math. We are not going to the math. So what was the activation function? We said it is G. So for the hidden layers, we mentioned this last time. Usually it is tangent hyperbolic, or nowadays we sometimes also use the rectified linear unit. Okay? And of course, for the output layer, let's say we call it F. This is usually the sigmoid or the softmax. Okay? So these functions are non-linear. And so these functions are non-linear in general. And the gradient of these functions dictate the gradient of the loss function. Of course, this gradient is computed for each node. The loss function is the sum for the gradient of all the nodes. ठीक है? So थोड़ा सा उसमें वो एक technical है issue, but let's, for simplicity, let's say कि they are directly, or at least they are related, but relation में थोड़ा सा उसमें वो complexity है कि multiple nodes भी हो सकते हैं. ठीक है? But let's say we don't worry about that. So they are related. So that's one thing. So the gradient of the loss function would depend on the gradient of the activation function. Okay? And if you look at the activation function, like the tangent hyperbolic or the sigmoid, it's like an S function. It saturates at the upper layer value and it saturates at the lower value. So gradient क्या होता है? Slope होती है. So slope ऊपर भी 0 हो जाएगी, इधर नीचे भी 0 हो जाएगी. So when the value reaches high side and low side, then the gradient will become 0. And while the value is 0, आपने पढ़ा था, then the gradient would be 1, close to 1. Middle पे वो gradient 1 है. So we have this notion of concept of plasticity or adaptability of a neural network. So a neural network would be highly adaptable if the gradients are close to 1 of the activation functions. In other words, the values lie in that narrow range. So let me draw that function. Okay. CP draw. Let's see. It's okay. So basically, you have the function like this. So you notice that the gradient, of course, in the middle is high, and of course, it becomes 0 as you reach on the right side when the value becomes large or when the value becomes low. So if the value lies in the middle range, you have some gradient. This is where the neural network is plastic or adaptable. And as the values becomes higher or lower, it would become its plasticity or its adaptability would be reduced. Okay? Because of course, the weights would not change because gradient will become 0. So, and of course, if you talk about the rectified linear unit, rectified linear unit is again non-linear. Rectified linear unit is also non-linear. So the rectified linear unit, of course, is this function. So this is linear. This part is linear. So if your activations lie in this range, of course, you will have a gradient. And of course, if it lies in this range, the gradient would be 0. So based on this, there are a couple of issues that typically arise in neural networks. And two issues, which of course we'll discuss later on as well, but since we're talking about it, we'll discuss it here. So one is, of course, the vanishing gradient problem. So vanishing gradient, of course, what does that mean? The gradient becomes 0. So if the gradient becomes 0, there will be no update in the network, and we will say that network is not abductable or is plastic, or it's not plastic. So this problem will typically become more severe if your network is deep. So that's why this is more common or popular concept nowadays, deep networks. What is a deep network? A deep network is one which has multiple layers. So let's say usually in the olden days, we just have 1 or 2 hidden layers. Now we may have 10, 12, 50, 100, especially in deep region, we might have even 100 hidden layers. Okay? So for deep network, remember in back propagation, error propagates from the output to the input. So the signal that is used to update the network starts at the output, but before it can reach the input, that signal and its strength becomes much weaker. So it's difficult to update the layers at the start of the network. And the reason, because the gradient there becomes either the value either becomes large or small, and the gradient becomes 0. Okay? So that is the vanishing gradient problem. So as such, maybe the last few layers may be adopted by the error, but the initial layers may not be adopted. So this is called the vanishing gradient problem. And this would typically arise in a deep network. So the other problem, we will discuss these solutions as we discuss neural network in the remaining part of this course. Some solutions to this. The other problem is exploding gradient problem, the opposite. I would call that gradient, I would say exploding value problem. So, so in this case, now from one iteration to the next iteration, the value of any given layer or any given unit in your neural networks increases. And it tends to increase or decrease both directions, could be positive or negative. So there is no bound on the values, goes on and increases and increases and increases. So this is also an issue, because if the value increases, you know that the gradient will become 0 and your network will not remain plastic. Okay? So this is another problem that can arise while you are training a neural network. Of course, for this problem, there's a very simple solution. You can simply clip the values on the upper and lower side. So maybe you can say that, so let's say we are talking about particular activation A. So if A is greater than, let's say, 10, then simply set A is equal to 1. Bring it down, or sorry, not 1, but 10. Clip it to 10. So any value above 10 would just be 10. We won't go beyond 10. Similarly, on the negative side, if A is less than minus 10, then set A is equal to minus 10. So usually this would work in most practical cases. Okay? So So exploding gradient problem does occur, and it does occur somewhat slightly more when you use the rectified linear unit. And you can see why it is, because rectified linear unit is unbounded on the upper side. But it can occur in the other situations as well, because activations depend on the input, not just that function. It depends on the input. Okay. So that's the exploding values problem. So we have talked about the loss function. We've talked about the stochastic gradient descent. We talked about error and error backpropagation. And we also talked about the issues of the vanishing gradient problem. And we also briefly talked about the exploding values problem. Uh, just trying to think, should I discuss all those things now or maybe later on? So we also need to discuss the issue of regularization, which is also relevant to logistic regression as well as to neural network. And but we can discuss this later on as well. Okay, maybe I think I'll discuss this later on. So let's, I think, finish this section and move on to vector, because that's also important. I wanted to start talking about embeddings and then come back to neural networks. Okay, any questions? All right. So, so we'll come back to neural networks again, because as I said at the start of this semester, neural networks is now a relatively big component of NLP. So, so far we have briefly discussed the feed-forward neural network. So later on we will discuss sequential neural networks like RNN, LSTM, GRU, and we'll also discuss contextual embeddings, which is a way of learning representations for words from neural networks. So we'll discuss that uh, after introducing the idea of embeddings. So let's start that. So vector representation. So representation is a fundamental, you can say, concept in computer science. So whenever we want to process anything using computers, we need to have appropriate presentations for the entities or objects that we want to process. So same is the case for machine learning and NLP. So in NLP, what we want to process are, as I mentioned before, are linguistic units. And linguistic units, depending on our understanding, could be anything from a single character to documents and corpus of documents. So linguistic units of interest could be of different sizes. So we would like to have representations for words that are expressive. So if we talk about the linguistic unit words that we have been discussing so far, so word is a linguistic unit. So far we had discussed words, let's say, as sequence of characters. So if I talk about the word itself, so it is W, then O, then R, then D. So these characters are written in some specific sequence. And of course, W comes before O, and then R, and then D. And we can use string processing to process such words. But of course, such sequence of characters do not convey anything about this word, or just they convey some basic things about this word, meaning that the spelling of this word. So W, O, R, and D. It conveys no meaning or other grammatical, you can say, rules that are associated with this word. So another representation that we discussed was simply you assign an ID to a word, to each word. So for example, the word, let's say, live would be maybe given an ID, let's say, word number 1335, for example, 1225. So this word of this ID doesn't tell us anything about this word. It just tells us this word is different from some other word. So maybe, so live, for example, let's say this is 1389. We only know that live has this ID and live has that ID. Those two words are not the same. That's it. We don't know anything else about them. What are their meanings? What are the differences, and so on. So this is, of course, a very basic way of representing words. Just trying to understand whether two words are same or not. While in the previous case, if you represent words as a sequence of characters, then maybe you have a little bit more information. Maybe you can do edit distance to find the similarity, as we discussed previously. But again, that is purely syntactic. It doesn't have any information regarding the meaning of those two words. Okay? So we would like to have expressive representations. So one way of having expressive representation is not have a vector for representing words. So vector is, of course, not just one value, it might be multiple values. Let's say a 300D vector. So now for the word live, you will have a 300D vector with values, let's say -1, 0.5, 1, 3, minus, let's say 1.5, and so on. Okay? So, of course, even by looking at it, this representation has multiple values, 300 values. So it can capture more information, right? It can capture more information. And of course, if you want to do it by hand, you might say that, let's say the first value is a value for, let's say, the POS, for example. What is the POS of this word? Maybe the second value, let's say, capture the connotation of this particular word. So let's say the third value, let's say, conveys the polarity of this word. And you can have other features representing this word, right? So for example, if I talk about polarity, the word good would have a value of, let's say, 1, and for this feature, and let the bad would have a value of, let's say, 0. Right? So good has a polarity, positive polarity, bad has a negative polarity. Similarly, if the two words are nouns, let's say if you have a chair, the feature noun, let's say feature noun has a value of 1. And let's say we have another table, let's say this is also a noun, this will be 1. And let's say we have another go, let's say this is a verb, let's say verb is 2. So you can do such kind of feature engineering to get richer representations for words. Okay? But of course, as you can see, you will have to do feature engineering more or less manually. You will have to define those features and then set appropriate values for those features for all the words in your corpus, which is, of course, not a trivial task. Okay? But the goal in doing this is, of course, to get expressive representations that capture more information regarding the unit, linguistic unit, rather than just being a simple ID. Okay? So if you think of words as vectors, then these are also sometimes called embeddings. So you might have heard about the name embedding. So the word embedding basically comes from the idea that if you have anything represented by features, let's say we have 2D feature, 1 and 2. So you have, so you can plot this 2D point in 2D space. So x-axis would be 1, y-axis would be 2, you will have a point at 1, 2. So this point represent a particular word, let's say, and you will have other words also. So let's say this word 1, 2. So let's say this is for the word D. Just an example. Let's say for the word A, you have, let's say 1, 3. And let's say for the word, let's say go, you have, let's say 3, 3, and so on. So all of these words would now be points in 2D space. So those points are, in other words, so that's where the name embedding comes from. We have embedded those words in space. Okay? So if two words are, let's say, somewhat related or similar, we talk about related and similarity shortly, then in space also they should be close together. Okay? So this is essentially the motivation for vector representations. We want expressive, richer representations that capture more information about the linguistic unit. And if we represent them by vectors, we can also, at least hypothetically, visualize them in space as points. And if 2 points are close together, then it means that those 2 linguistic units, like words, would be similar in some context. Okay. So that's the introduction for vector representations. So a little bit of so I think we can talk about that later. So let's move on. So one way of quantifying or identifying or discerning the meaning of a word is by looking at the words around that word in large amounts of data. So in other words, the meaning of words is, you can say, characterized or even defined in some way by the words around them in running text. Okay? So for example, if I talk about the word, let's say, so if I talk about the word student, so usually student, the word student would occur oftentimes close to other words like, for example, course, university, uh, and let's say even calculator, and so on. So these words would be used in close proximity to each other in large amounts of text that you have collected uh, in a particular language. Okay? So what we would like to do is we would like to exploit this information to get richer representations automatically. Okay? And this idea of words meaning being defined by the words around them is generally called a distributional semantics hypothesis. Distributional in the sense that in probabilistic sense. So if one word, for example, the word student is very likely to occur or frequently occurs with course, then these two words are likely to be related. Okay? So this is known as the distributional semantics. Of course, this idea was known for a long time. I think it was first popularly identified in the 1950s. But I think in the 2000, this idea really came into being from a computer science perspective. So now distributional semantics is like uh, fundamental to almost all NLP tasks. So we tend to learn about words and about language from what has already been written in automatic way. We don't ask linguists. We let automatic tools try to understand the rules of the language or other things about the language from what has already been written. So this is basically called distributional semantics. Okay. By the way, ये मैंने semantics लिखा है, distributional linguistic है in general. So semantics is specifically about meaning, and you can generalize it to all linguistics. Okay. Distributional linguistic. All right. So now let's start with some basic representations. So in general, we can have two types of representations. We can have sparse representations. Again, we are talking about vector representations. So vectors are sparse, or so you can have representations that are sparse or vectors that are sparse and representations that are dense. So sparse means that there are many values that are zero in the representation, while in dense, it means that most values are non-zero. Okay? So we'll first start with the basic representations, and those are usually sparse, and then move on to the dense representation, which leads to the more modern techniques, for example, the word-to-vec, and then later on, we'll discuss a few others as well. So how can we build a representation for words? So let's say we have word. So far, uh, so usually what we have in NLP is you have a corpus of documents or some large linguistic units. Okay? And of course, within those documents, you have words. And whenever we talk about documents, it's a linguistic unit that has coherent information. So usually when talk about a document, it's usually coherent. So you take a paper, research paper, it generally talks about more or less one topic. Okay. So, and of course, if you process all those documents, you get the vocab, okay, which we have discussed before. So vocab is, of course, the distinct words that are used in all those documents. So, and then you can create a word by document matrix. Sometimes this is also called term by document matrix. So word की जगह term हम भी use कर सकते हैं. ठीक है? So what would this be? Let's say you have 3 documents, let's say D1, D2, and D3. Okay? And let's say we talk about some word, let's say D, and let's say Lahore, and let's say science. Okay? So D, of course, is a word. Now we basically count the number of times D occurs in D1. So let's say it occurs 10 times. How many times it occurs in D2? Let's say 25 times. How many times it occurs in D3? Let's say 15 times. So what about Lahore? So Lahore, let's say in D1 it occurs 5 times. In D2 it occurs, let's say 0 times. In D3 it occurs, let's say 0 times. So what about science? In 0, 1, and let's say 5. So you can have this matrix. So this is now a 2D matrix, which we call a term by document matrix. Okay? So now this matrix captures more detailed information about words and documents. Okay? So if you talk about the word, for example, D, So if you talk about the word science, for example, so science does not occur in document 1, it occurs in document 2 once and 5 times in document 3. Okay? And if you compare this with, for example, the word Lahore, Lahore only occurs in document 1. So in a way, you can say that science and Lahore are not very similar because they do not occur in the same document. Again, the distributional semantics comes into play, right? And similarly, if you now actually I was looking at two words. Now you can actually also look at two documents. If I look at document D1, D1 has the word D and the word science and no word science. The word D and the word Lahore, but doesn't have the word science. If I look at the document D3, D3 also has D and it has the word science, but no Lahore. So in this way, you can also compare documents also based on the words that appear in them. So you can compare words based on their occurrences in different documents, and you can compare documents based on the words that appear in them. Again, two different notions of distributional semantics or similarity. Okay? So how can you quantify this similarity? Typically in NLP, we use the cosine similarity. And more generally, I'll talk about this later on, I'll call this relatedness. Because similarity usually means a slightly different thing, and relatedness, it's a more general term. So we'll come to that later on, maybe in the next class. Okay? So cosine of, let's say I have the मेरे पास था लाहौर. लाहौर का वेक्टर क्या बना फिर हमारे पास 1 0 0. एंड व्हाट अबाउट साइंस? साइंस का वेक्टर मेरे पास बना था साइंस में क्या था 0 1 5. So science is 0 1 and 5. So these are now two vectors, and you can think of these as vector representations of words. How did we get these? By counting their occurrences in different documents. And if you want to find the similarity between them, you simply find the cosine between them. So cosine is simply, let's say, एक मेरे पास था Lahore. Let's say the vector is L. Take the inner product with the vector of science, which is S. And then, of course, you have to normalize it because L and S may be of different lengths. So cosine में normalization इसकी norm से होती है. So of L of S. ठीक है? L2 norm, or the length of S, L, the vector L and the length of vector S. This is in a denominator. So this actually is, you can say, the normalized dot product, which is actually the cosine of the angle between these two vectors if they are represented in space, or if these two points, which are embeddings, so basically these are 2 points and the vectors would be from the origin. So let's say a point science का है, ये point लाहौर का है, वेक्टर क्या होगा, origin से इधर वेक्टर आ रहा है, इधर से इधर आ रहा है. So ये जो हमने निकाला है cosine, this is essentially the angle between the two. So if this angle is small, meaning that if they are collinear, these two vectors are collinear, then we say that they are highly related. But if they are 90-degree apart, in which case cosine would be 0, then they are not related. So we can quantify the relatedness using the cosine similarity. I think I'll stop here. So next class, so this is, by the way, is chapter 6 of your textbook, vector representations. Next class will continue with this discussion, talk about word by word matrices, word context matrices. We'll talk about PPMI, and then we move on to skipgrams, which are based on neural networks. Okay. Sorry, the word to vec, and of course skipgrams, which are based on neural networks. Okay. So any questions? Any questions? No, maybe not. So in the next week, I think we can have the quiz on Tuesday if you like. So Tuesdays को हम फिर routine शुरू कर देंगे. Is that fine? किसी का कोई comment है इसके ऊपर?
सर ट्यूसडे से नहीं थर्सडे से ही कर लें ट्यूसडेज को हमारा ना एक और क्विज होता है तो फिर तैयारी सही नहीं हो पाती
अच्छा ठीक है ट्यूसडे का मेरा दूसरा कोर्स भी है पीपल आर टेकिंग बोथ दिस कोर्सेज दोनों का ट्यूसडे को होगा ठीक है आई डोंट हैव एनी इशू पुरानी वाली रूटीन ही हम रखें थर्सडेज को
यस सर
ठीक है तो फिर जो डेटा
फिर
माइनिंग ले रहे हैं उनका फिर ट्यूसडे का ही चलेगा तो वही पुरानी रूटीन चलेगी ठीक है सो दैट्स फाइन विद मी तो एट द स्टार्ट आई आल्सो मेंशन कि आपको प्रोजेक्ट मैं आपको अनाउंस कर दूंगा बट गो हेड एंड फॉर्म ग्रुप्स ऑफ अप टू 3 people for project this year would be slightly less involved. Essentially, I want you to look at some recent papers, maybe 2, 3, 4 papers, and just implement, reduplicate one of those papers. तो ये एक टास्क है इस बार आपका प्रोजेक्ट का तो ज़्यादा डिटेल लिटरेचर रिव्यू या मेथोडोलॉजी पे मैं आपको नहीं फंसाऊंगा पर यूजुअली सेमेस्टर छोटा होता है तो हो नहीं पाता yes, no, you can do it up to even one individuals can do it. So max is 3. ठीक चलें फिर मेरे ख्याल से I think that is all from my side. Please restart your routine of reading and following up the lectures immediately after we have covered them because that would help you prepare for the quizzes as well as the exams. तो डिले ना किया करें immediately पढ़ लिया करो बुक आपके पास सिर्फ एक ही है थैंकफुली तो क्विकली पढ़ लिया करें उसको भी because strictly उस रूटीन से मैं पढ़ा नहीं रहा होता जिसमें बुक पे but book does have some more details and some other things that are often very useful. ठीक है चलें जी